Chapter 2, Exercise 2.79, Part A, Ultraviolet radiation and radiation of shorter wavelengths can damage biological molecules because they carry enough energy to break bonds. A carbon-nitrogen bond requires 305 kJ per mole to break. What's the longest wavelength of radiation with enough energy to break carbon-nitrogen bonds? So here's the plan. It takes 305 kJ to break 1 mole carbon-nitrogen bonds. So to break one single carbon-nitrogen bond, how much energy is required? It's going to be 305 kJ divided by the Avogadro constant. And then we get the energy enough to break one bond. We can convert that energy to the frequency of a photon. How? That energy divided by the Planck constant, we get frequency. And then given the frequency, we can calculate the wavelength. How? It's the speed of light divided by the frequency. We'll get wavelengths. Likely in the SI unit meters, and then we convert meters to nanometers here. Alright, and we keep 3 significant figures. According to the rules of 6 figures, since we're doing multiplication and division, we will keep 3 figures in the end. So now the first step is this, 305 kilojoules. Kilo is 1,000. Per mole bonds. So I'm going to find out the amount of energy to break one single carbon-nitrogen bond. It's going to be this much. 5 times 10 to the power of negative 19 joule. Right? So I'm going to put the unit here just for now. And I need to convert it to frequency, because the energy of a photon equals the Planck constant times its frequency. So to get the frequency, it's the energy divided by the Planck constant. The unit is joule second. Alright, after we do this calculation, we'll see the unit is going to be 1/second, or hertz. That's the frequency. Now I'm going to remove the units, because Wolfram Alpha may not be able to handle the units properly. But keep this in mind. Whatever you see here is the frequency of the photon. And how do we get the wavelengths given the frequency? Well, given the frequency, we can calculate the wavelengths this way. It's going to be the speed of light divided by the frequency. Now we have the wavelengths. But this wavelength is in meters, not nanometers. 1 meter is 10 to the power of 9 nanometers. So I will multiply this by 1 to the power of 1 times 10 to the power of 9. This is to convert from meters to nanometers. We have a number 392 here. That's the wavelength. You can see the calculation over here. Again, this is the amount of energy to break 1 mole bonds. And then over here, I got the energy required to break one single bond. And then this is also the energy of the photon that's needed to break the bond. And then over here, the energy of the photon divided by the Planck constant. I got the frequency. So what's highlighted is the frequency in the SI unit. Now the speed of light divided by the frequency, we get the wavelength in meters. Finally, I convert meter to nanometers. So it's going to be 392 nanometers. And this is indeed ultraviolet. What kind of photons have even higher energy than ultraviolet? X-rays. Let's look at mastering chemistry. We need to know this equation. The energy of the photon is hc over lambda. All right. And how did they get this? Well, this is the amount of energy needed to break one bond, one single bond, not one more bonds. And this is how you compute lambda. Finally, they also convert meters to nanometers in the end.